Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this lesson we discuss the electrical conductivity of acid, base and salt solutions and then wrap up the topic by comparing the reactivity of strong and weak acids.
Is about conductivity. About solutions, it may be salt solutions from a neutralization reactions, or it might be acids and it might be bases. First thing is we need to say what is the requirement for something to conduct. Okay, so this is what we're talking about. Is we would have a solution of a chemical. We put electrodes either side of it and connect that through to a battery, and then have a light in it. And if it's conducting through the solution, then the light will come on. That's basically what we mean. Okay, and there's something that has to be present if that is going to happen. Does anybody know what the requirement for something to conduct electricity is? Free-flowing electrons is partially right. Nearly there, because there's no free-flowing electrons there. But in a wire, they are freely moving electrons, because that's the property of a metal, and we'll see how next topic. Okay? But for the moment, there are no free-moving electrons, but there are free-moving charges. And those charges are in the form of ions. So in other words, to conduct electricity, the formal way of writing it is there must be freely moving charged particles. Yeah? The charged particles we're dealing with are not electrons, but they can be electrons. They are ions in solution. Okay? And that's something that you should write out straight away. If there's a question on conductivity, say, for something to conduct electricity, there must be freely moving charged particles. In this case, ions in solution. Okay, so it's all about the ions in solution. The higher the concentration of ions in solution, the better the conductivity. Okay? And that's the all-important thing. Okay? You need to be looking at concentrations of ions in solution. And there's a sort of a blinkering effect that can occur here if you're not careful. In that people start to think about strong and weak acids, and they're thinking about dissociation into ions. And strong acids and strong bases fully dissociated to ions, good conductivity. Weak acids, on the other hand, tend to be only partially dissociated, and so they only have low concentrations of ions, so they're poor conductors. Be very careful. The first thing to look at is what type of substance are we dealing with, because we're looking at concentrations of ions. Okay? And we've already seen that we can have very weak bases. Here is an example of a weak base, but it's ionic. So you're going to have high concentrations of ions when you dissolve this up. It doesn't matter about the dissociation being partial or not. You've already got tons of ions from the nature of the compound itself, because it's ionic. So the first thing to look at is the substance that they're showing you on the paper, if it's a test, is it ionic? Any ionic compound is going to be a good conductor, because there's going to be high concentrations of ions. Full stop. Don't go any further. You don't need to talk about dissociation because it's already ionic. Okay? So all salts are good conductors. So that's the first thing to say, that if it's an ionic substance, don't even look to see whether it's acidic or basic. Doesn't matter. It doesn't matter if it's a strong or weak acid or base. Just say it's an ionic salt. When you dissolve it in water, those ions separate fully from one another. You get high concentrations of ions, and so you are looking at a very good conductor. Yeah? Next, we need to look at strong acids and bases. Okay? All important words. Fully dissociate. Concentrations of ions are high. Good electrical conductors. Partially dissociate. Concentrations of ions are low. So they are poor electrical conductors. Notice it's poor. They aren't insulators because there are some ions there. So there's something to carry the charge. It's not much. So they're not very good. But if you were to put a circuit, put them as part of a circuit, you'd see the light very faintly lighting up. Okay. So the first thing, as I say, is ionic salts. Look for the ionic salts. They always give you one. Do not talk about partial dissociation or anything in terms of weak acid and bases. Just say that they fully dissociate into ions when you dissolve them in water. Okay? And then you're there. What we're doing at the end of this topic is tying weak and strong acids to various properties and various outcomes. And one of the things we looked at was the pH of salts, of the conjugate acids or bases of weak acids, strong acids. We also have tied a dissociation of strong and weak acids, or degree of dissociation, to conductivity. Because if you remember, the requirement for something to conduct is there must be freely moving charged particles. Now, in the example of solutions, what we're looking at are freely moving charged ions. Charged particles are ions, and in solution they can freely move. And so we have available to us a tool which basically will tell us the level of concentration of ions in a solution. So if you've got a good, highly conducting solution, then it's telling you about a high concentration of ions in solution. If you've got a poor conductor, then there's only a low concentration of ions. And that's the sort of situation you have when you're distinguishing between strong and weak acids. You haven't got this continuous spectrum. You've either got a low concentration or a high concentration. And we can tie that directly to the strength of the acid or base, with the clear proviso that you need to be very careful. Before you start doing that, you need to look at the nature of the compound. And if you're dealing with an ionic compound that happens to be a strong acid, a weak acid or weak base, or strong acid, strong base, it's irrelevant about the degree of dissociation because it's ionic, and therefore, if it dissolves up in solution, you're going to get high concentrations of ions. So it's going to be a good conductor. So any ionic compound that's soluble will give a highly conducting solution. And that's the first port of call, if you like, when you're looking at these things. Is it ionic? If so, it dissociates freely into ions, or dissociates completely into ions when added to water, so it's going to be a good conductor. If, however, you then look at something that's a neutral molecule, which you're going to add to water, then it could be one of two things. It could be something like HCl, and that's a strong acid which completely dissociates, so you get high conductivity. On the other hand, it could be something like ammonia, which is a weak base. It only partially dissociates. You get low concentrations of ions, and so it's only a poor conductor. And that was the way we linked conductivity to concentrations of ions, which in turn we linked to strong and weak acids and bases. The final piece in the jigsaw is one thing that just relates really to acids, and it's something that brings us round full circle to the beginning of the topic and rates of reactions. And it's something that actually makes use of what you did in year 11 with acids and bases. And that is that if you look at acids, acids actually do a series of reactions with other substances. So, for example, we know they react with bases, but what about with metals? Okay, so that's another example. So let's write that out. It's a typical reaction of an acid with a metal. So we And the easy way to remember this is MASH. Use the acronym MASH. Metal plus acid, salt plus hydrogen. And the classic example we'll use is two of those. Okay. And that's an example of a reaction with a strong acid. And zinc's the classic one we use. It's one you can carry out in the classroom because you use zinc granules and it bubbles away quite nicely and you can follow the reaction. Okay. Now, all acids do this, whether they're strong or weak. Okay. So this is a strong acid. Let's label that as a strong acid. Let's take a weak acid like methanoic acid. Okay. So that's a weak acid. And it's exactly the same type of reaction. The question is, if we've got a strong acid and a weak acid, and you are giving off hydrogen here, which one of the two is going to give off more hydrogen gas? Okay. Is it going to be the strong acid or the weak acid?
Are any weak acid or any of these reversible?
No, it's a one-way reaction. Remember this. And the reason, that's a good question, very good question. What we're going to do is just let the hydrogen bubble off. So it's just going to push it right over it. If it's going to. So what's the thing? Which one will give more hydrogen? The weak acid or the strong acid? And that's what everybody says.
Will it be the same?
They'll be the same. Because what this is telling you is if I take 2 moles of that and I react it with 1 mole of that, I only get 1 mole of that and 1 mole of that. This is telling me I get exactly the same. 2 moles of that react with 1 mole of that to give 1 mole of that and 1 mole of that. And that was a great question that was asked. Are these one-way reactions? And the answer is yes, they are. So they produce the same quantity of product. So it's the reaction that determines it, not the strength of the acid. Okay? And we'll look at it in just a second as to why this works like this. Okay? So, of course, there's a provisor here. We're using the same concentrations and we're using the same amounts. But if given the same amounts, the amount of hydrogen that you produce at the end is not dependent upon the strength of the acid. Okay? Same volume of hydrogen. And that's the reason why. It's dependent wholly on the ratio of moles in the equation. Because it's 2 to 1 gives 1 to 1, 2 to 1 gives 1 to 1, then you're going to get exactly the same volume of hydrogen. That's the controlling factor. It's what we call the stoichiometry of the reaction. The relative mole quantities involved. Okay? That's what determines it. Okay? Now, let's have a look at what actually happens. What we're looking at here is the overall equation for the reaction. Okay? This is the overall equation. In fact, this is really a 2-step process. Because we know when we add that to water, that actually dissociates completely in this case because it's a strong acid. So, okay? So, what we're doing is we're reacting 2 different acids with a metal. The actual part that reacts with the metal is not the whole acid, it's just the H3O plus here that's produced. Okay? So, the second step is this is the actual reaction between the acid and the metal. And it's the same for both acids. Because all acid is doing is producing hydronium. What's the difference though? Now, what's going to be the difference between a strong and weak acid? What's the big difference here?
One partially dissociates.
One only partially dissociates. So what's going to be the difference between this and this?
The speed, the time taken.
Yeah, but why? What am I looking at that's actually going to be a big difference here?
The concentration.
H3O concentration. Good. So the only difference is this is going to have a high concentration of H3O plus. So why don't we put that? High. Come. Whereas the other one is going to have a low concentration because it only partially dissociates. Okay? Low concentration. But both of them produce the reactive part. What's the difference going to be here then with this reaction? We've said you're going to get the same quantities, but what's going to be the difference? How will we know which one's the weak acid and which one's the strong acid? What will we see that's different? The time taken or the rate of reaction. In this case, where you've got a high concentration of H3O plus, you've got all of this available immediately. And so you're going to have a high concentration of H3O plus, so it's going to be a fast reaction. Okay? This is going to have a low concentration. But what's going to happen when this starts reacting away to this equation? Ah, somebody's doing this. In other words, Le Chatelier's principle will start coming in. If you start taking this away, these two will react together to form more. And it'll react away. And so more and more will be produced until it's fully tipped over this way because you're pulling it away all the time. So it will continue to react until all of this is dissociated. So that's why it doesn't make any difference whether it's a strong or weak acid. You'll still get the same volume of hydrogen produced. It's just that it's a lot slower with a weak acid than it is with a strong acid. That's the only difference. I'll write it out a bit more carefully. Yeah? So you're forming Zn2 plus AQ plus H2 gas plus 2H2O with an L, not an E. Okay? So that's what we've got to... Now, the first thing to say is this is the same reaction for both acids. This one. Okay, so both acids use that equation as the second step. So the only difference is that each acid is producing H3O plus. The H3O plus then reacts on the surface of the metal. Okay? So what we have, so let's have a look at the strong acid. Okay, so that's our starting point for this reaction here. Okay, is that for a strong acid, okay, so for a strong acid, we've got a high concentration of H3O plus. This means a high frequency of collisions between reacting particles here. With the weak acid, okay, the weak acid now, partial dissociation. So the concentration of H3O plus is low. That means low frequency of this effective collisions. And so, and this is the point, a slower reaction rate. That's the big deal. Okay? The slower reaction rate. Whereas before, reaction's fast, now you've got a slow reaction. However, let's follow this through. As H3O plus is used up, it is replaced because you're losing equilibrium. This one that we're talking about, this reaction here, okay, that's the acid dissociation reaction. So in other words, if you start with the same quantity of strong acid and weak acid, you're going to use both of them up. In the case of the strong acid, you're going to use the up instantly because you're producing all the H3O plus in one go, which then reacts and produces a volume of hydrogen. In the case of the weak acid, you're drip feeding the reaction, but you're going to still use it all up, but only gradually. So you'll still produce the same volume of hydrogen, it's just over a longer period of time. Okay? Okay, so that's it. And that really is the end, as it were.